Thank you very much, Mr. Chairman, for that kind and warm introduction. Good evening, ladies and gentlemen. May I say it's a great pleasure to be here again in Singapore. Over the years, with my sort of interest in audio, it's brought me to quite a few places in the world overall. I never seem to stay in one of them very long, but it's brought me to quite a few places. And there are probably 3 places which have had special meaning to me. The first is Morocco, Marrakesh. And the reason for that is it's somewhere I've visited many times, but actually many of my publications and much of my research, because it's an area where I've been able to think and contemplate, it's somewhere where many ideas have been seeded, so it's particular importance to me. Another place I love is a little place called Riva, which is in Lake Garda. The wine, the scenery is delightful. It's a good place to relax. And third, but certainly not last, is Singapore. I have a particular, many pleasant memories, both of being with Singapore and also over the years teaching many Singapore students. At Essex, particularly in the 1980s, we used to have significant numbers of Singapore students come. And I can say almost without exception, and I include Stephen here, that they were hard-working, conscientious, and model students in every respect, and a pleasure to teach. And when I come here, I find some of the friendliest people that I've met on the planet. So congratulations to you all. Whatever you're doing in Singapore, you're doing very, very well indeed. And you certainly, for a visitor like me, to be able to come here and sample your culture is a real privilege. My career has spanned slightly more years than I care to mention. I started my career, shall I say, in 1971 at Essex, so I've actually been there quite a long time. And my main focus of research has been specifically in the field of audio engineering, though I have dabbled in other areas, including TV systems and stuff over the years. And audio, in particular, has been an interest, not only because I think that it adds something culturally to the world. It really does have significance. It allows our legacy of music to be appreciated by many people, and this is very important. But also as an exercise in electronics, I find it a very challenging area, because if you look at some of the high-performance systems, particularly with the new high-resolution formats which are emerging, these are very, very demanding upon the precision and the design and the electronic parts which are used. So it is a challenge, and it continues to be a challenge. We are seeing new emerging standards. We're now seeing integration with network systems, for example. So the challenges continue. On Monday night, I'd only arrived on late Sunday evening, so if I have moments of distance, please, I apologize, because my mind probably isn't fully engaged yet from traveling a fairly long distance. But on Monday evening, I was feeling a bit restless about pretty near midnight, actually. So I went down into the lobby of the hotel and started dabbling with the internet and just seeing what I could come up with. And I foolishly dialed in my name to see what sort of comments were out there. And I came across a website, one of these chat rooms where various people say what they feel. And this one was populated by some of the best analog audio designers, people like John Curl, who designed para-sound amplification. And they were having a discussion. And much to my amazement, the topic they were discussing was an amplifier concept which I'd invented in the late 1970s and published in the AES in the early 1980s. And it was on error feedback to reduce crossover distortion in power amplifiers. And to find what must be 25 years later, this topic being debated still, amused me somewhat. I'm glad to see that it had some significance to these guys. But the thing which caught my mind more than anything was there was one contributor who actually acknowledged the fact that he'd been a student 20 or 30 years earlier at Essex University, where I work. And he made the comment that even in those days, Malcolm Hawksford was truly eccentric, or words to that effect. So nothing's changed, I hate to say. I've always had that slight reputation. Anyway, what I want to do tonight is not to completely give you all the answers to this subject, but I want to talk about the ideas of what might be perceived as a digital loudspeaker system. Now, I'm going to do this initially by looking at the evolution of how conventional speakers have developed, and then looking at what may be conceived as a digital loudspeaker system. Now, as I say, I do not have complete solutions to this problem, but maybe seeding the ideas here might help people start thinking about this. So let me emphasize that this is very much my own perception. The ideas may be fundamentally flawed. They may have to evolve in order to make something truly practical, but you've got to start somewhere. And so this is to say, if you could actually implement certain key parts and do sufficient signal processing, we have some opportunities to produce maybe something quite exciting. So let's make a start. Well, history. We started off with mono, signals being played on a standard shellac disc. Evolution of stereo. You see some early developments of a stereophonic system. I worry a little bit about this guy. But there is for the ladies in the audience, you might be more interested in the female version of this augmented stereo reproduction system. Actually, I'm not quite, to be fair, I'm using these slides without knowing their true origin. So anyone out there who recognizes them, I apologize for not referencing their source. I actually feel that this system may well have been developed in the Second World War, and I suspect what it's actually there is for someone to stand on a cliff top and hear enemy aircraft coming in from a distance. So I'm not quite sure it was designed to listen to the new high-resolution audio formats which are emerging. Now we're going to talk about array loudspeakers, so I'd like to show you an early version of one of these systems. We see a collection of various horn loudspeakers, horn probably being the correct choice, because I look more closely and I actually don't think it's relevant at all. I think they're actually car horns. These look like something out of an old Bentley, possibly. So this is the early stages. We come up a little more modern. Those of you who may have seen, these are avant-garde speakers. I think they're made in Germany. I show it because it just looks plain impressive. I mean, that's the only reason, really, for showing this slide. But this is well, I suppose it's a four-way system. There's actually three large horns, a high-frequency, mid-range, and a lower-frequency unit, plus this huge horn-loaded systems. I don't know if anyone here has heard full-range horn loudspeakers. They're a very strange beast. The advantage of them is that they're incredibly sensitive. You know, you can have a 20, 30, 40% efficiency if you design them properly, which means they can produce loud noises on a little amplifier, probably not much bigger than a matchbox. Most loudspeakers which populate our homes, you're lucky if you have a 1 or 2% efficiency. So most of the power when you buy your 500-watt Krell or whatever it may be is not going into acoustic power. So one advantage that horn-loaded systems have is that they have such high efficiency that they're very low demand on amplifiers in terms of power rating. Now let's get closer to home. I hope you've all been impressed by the very excellent system which has been implemented here at SIM. It uses, as you've seen, B&W loudspeakers, a well-known British loudspeaker company. And this particular slide doesn't show the speaker system you saw, the 801s tonight. It shows a slightly lower model in their range, although to be fair, the center speaker, I think, is the same one, if I'm not mistaken. So this is a high-quality system, a really high-quality system, which shows the sort of state of play as things are at the moment. And one thing which has changed in loudspeakers in recent years is the ability to build complex shapes. For example, you can see that these speakers are actually curved. And they're not just curved to make them look aesthetically pleasing, they're curved for good acoustical reasons. One of the important characteristics which is now recognized with loudspeakers is the ability to be able to maintain a well-balanced polar response over quite a wide frequency range. So having a narrow baffle front and having curvature that looks a little bit like a teardrop is known to be a fairly optimum shape. In fact, at high frequency, where the wavelength of sound is very small, it's possible to implement something such as the tweeter, which we see on the top of the center speaker. You can also see one on top of the column speaker as well. And that really does have this sort of acoustic form of a teardrop. And the reason it's that shape is that as the cone radiates sound into space, the wavefront follows this sort of expanding near-spherical baffle edge and produces a very well-behaved polar distribution. There are no discontinuities as the wavefront expands from the front of the drive unit. If we have a classic rectangular box, the wave moves out across the surface, it meets the discontinuity at the baffle edge, and you get secondary radiation from there, which then causes interference and degradation in the polar response. So that type of loudspeaker is designed with very good scientific reasons. Of course, at low frequency, where wavelength is long, subwoofers really don't have to be formed that way. So the bottom unit we see, which would be typically implemented in a 5.1 system, where the 0.1 feeds the low frequency signals to the base unit to either give natural extension in terms of music, or if there are sound effects, to obviously give the low frequency sound effects. The LFE channel, as it's called, is the low frequency effects channel. Now, the surround speakers are actually quite interesting as well, and we see a typical B&W surround speaker. I think this is very similar to the ones you would have heard tonight as well. Now, because in a 5-channel system, it is limited. I mean, we only have 2 speakers which have to give both side and rear information. There is a necessity sometimes for the sound field produced from the rear speaker to have both direct sound attributes, but also somewhat diffuse attributes as well. And this particular speaker will have a direct facing bass mid-range, a high frequency tweeter, and on the side, it's actually got side radiating speakers, which can be configured to give somewhat more of a dipole radiation. So there's less direct sound and more ambience created. Depends very much on the application, but you can actually switch the configuration of this speaker to match the conditions which you require. Now, I'm sure you all are familiar with the reasons why loudspeakers have multiple drive units. Obviously, at low frequency, we've got to move substantial air to generate appropriate sound pressure levels. But also, it turns out, where you have a direct drive unit, the bandwidth over which that drive unit can operate is dependent upon its physical size. And ultimately, there will be 2 limitations, which are linked to the physical parameters of the drive unit. At low frequency, there will be the fundamental resonance, and I'll say more about this in a little while, below which the output starts to fall. This is a pure mechanical resonance formed by the mass of the cone and the compliance of the suspension, rather like a weight bobbing on a spring, same sort of principle. But at high frequency, where the wavelength becomes comparable with the diameter of the loudspeaker, effects on polar response and radiation take place, which cause the output from the loudspeaker to deteriorate. So at high frequency, we want to make the radiation area smaller. And again, when we start talking about some of these physical structures I'm going to introduce, the need to produce something smaller at high frequency still persists, even if we look at something which may be considered a digital loudspeaker. So in such a structure, we need at least 2 and often 3 drive units to handle different parts of the frequency spectrum, and that obviously requires filters. So just a quick look inside. You can actually see the construction of these drive units. This is a very typical or high-quality bass mid-range unit, mainly used in mid-range in the B&W implementation. I think it's got a Kevlar cone. You can see the magnet assembly on the back. You can see both the outer surround and the inner spider, which hold the drive unit, the radiating surface in place. And there's a phase plug to enhance the higher frequency polar distribution. The tweeter, again, there you can see very easily here the sort of teardrop like baffle shape, which is designed to improve diffraction performance, and the internal mechanism, the dust cover, the actual radiating area, the compliance suspension, the speech coil, and then the magnet assembly at the end. All these are coupled together. I think it's in the incarnation of this speaker, which you saw today, the actual radiating surface is covered with synthetic diamond. So they actually synthesized diamond to make a very hard neopistonic radiating cone, which has incredibly good high-frequency performance. Just looking inside, you can see those internal mechanisms. And again, I show this because it will impact on how we look to put together a sort of digital loudspeaker array. But let's just look at the fundamentals. Here we see the outer surround. Here we see the cone, the speech coil, which is embedded in this magnet. The main magnet is here. The purpose of the magnet is to energize this part of the circuit so that magnetic flux flows through the back plane into the pole piece and more or less at right angles across the air gap. And we all know, hopefully, from fundamental electromagnetics theory, that when current flows in a coil, and if that current is at right angles to the magnetic flux, we get a force which is in the plane, at right angles to the plane of the magnetic flux and the current distribution, which fortunately in this configuration is along the axis of the cone. So it produces a motor which causes the cone to move backwards and forwards. Possibly lesser known is the fact that when the cone moves, it actually operates as a generator as well. So when the cone moves backwards and forwards, the fact that these current-carrying conductors are cutting lines of magnetic flux cause an induction of EMF in the coil, which then affects the current which flows in the speech coil. So there's a sort of interaction between motor and generator effect. And getting the right response of the speaker, that interaction is actually very important. The spider assembly, which we saw earlier, is here. So effectively, the cone is mounted at 2 points, one by the compliance suspension here and here, and secondly, by this compliance suspension, often called the spider, which has high resistance to motion that way, but nice compliant motion along the axis of the speaker. So that holds the cone rigid, so it doesn't wobble and scrape the pole pieces of the loudspeaker motor assembly. So that's basically what we see in a conventional drive unit. Signal processing-wise, if we're going to have 2 or more drive units, we have to design crossover networks, and there's a lot of literature on the design of crossover networks. But putting it fairly simply, in the analog domain, we can treat the low pass and high pass as analog filters, and we need to design the circuit such that when we add together the low pass and high pass transfer function, that the composite frequency response is as flat as possible. Now, it turns out with analog design that in order to get reasonable degrees of freedom in the design of these filters, that the normal practice is to sum the 2 results to an all-pass filter or a time delay. Ideally, it should be a time delay, in which case you get perfect wavefront reconstruction. But in an analog system, this is often weakened to an all-pass filter. So you get a flat amplitude response, but you get a nonlinear phase response. It's just the way analog circuits come about, because they tend to solve first-order type differential equations. And so it's easier to get an all-pass response than it is to get a constant time delay. Synthesizing constant time delay with linear analog circuits is only ever approximate and quite difficult. It turns out, however, that if the degree of phase distortion is minor, then the subjective consequences of having nonlinear phase are not too problematic. And we end up with a flat amplitude response, which is very critical. However, let's start to introduce some digital ideas. If we translate this to the digital domain, so I'm now using Z, it's much easier to implement this. We can get 2 digital filters which clearly can be summed to produce a constant time delay. So theoretically, at least, using DSP, a much more accurate response can be achieved. So maybe the first move towards digitizing a loudspeaker relates to processing the signals in the digital domain prior to the drive unit. So we do away as much as possible with the analog processing and substitute high-performance digital filters. Now, this sort of approach emerged in the 1980s. I certainly worked on it with some research students in the 1980s. There were companies like Meridian who were also competitively working at this. But I was fortunate enough to work with Canon at the time in Japan, and we actually produced in the mid-1980s a prototype digital and active system which was taken to Japan. Now, normally electronics flows the other way from Japan to the rest of the world, but here was one example where we were able to demonstrate, at least in concept form, a DSP-enabled active loudspeaker system. And this shows the general structure. Now, this is not what I'd call a digital loudspeaker. I'd call this a digital and active loudspeaker. Typically, we would take a digital input source from a CD player or other digital source, and there would be, let's just look at a two-way system, two paths with DSP in each path. So we would have a filter. Now, we found it convenient, for various reasons, which I'm not going to go into now, to split the task into two filters, one which effectively got the amplitude response to match our target crossover. It also took into account errors in the transfer function of the drive units. So this was both an equalizer and a way of achieving the appropriate crossover filter. These were typically designed as minimum phase filters. But it turns out, due to time delay and various things and the transfer function of drive units, that they're not quite minimum phase. So we used FIR phase equalization to compensate for any phase distortion. So the design process would work out the required amplitude response. It would use minimum phase theory to compute then an appropriate stable transfer function, which could be implemented with an AIR realization. And then it would compare that filter with the actual required phase response and design a flat amplitude compensating FIR filter. So that was the process. Now, the output of those filters is then fed to an individual D to A converter. The beauty of this is that these converters now only operate over a fraction of the audio bandwidth, so increase their dynamic range effectively because the energy is split. And also, any intermodulation distortion, because the bandwidth isn't full band, the distortion performance tends to improve as well if there's any imperfections in the D to A converter. Typically, D to A converters produce an output current. They're usually output current devices. And that current has to be normally converted to a voltage. So there is a need for a very high quality current to voltage converter stage or transconductance amplifier bolted to the output of the D to A converter. That could be as simple as a virtual operational amplifier, or it could be a little bit more sophisticated. We designed our own discrete circuit to try and do that job as accurately as possible. And again, for reasons I don't want to start to talk about now, I believe this particular circuit is extraordinarily critical in getting good performance in CD players and digital electronics. And it's often one which gets compromised by maybe inappropriate components being used, or at least, shall we say, cheaper components being used than should be. Any distortion here, because it has to deal with broadband signals from the D to A converter, can introduce little amounts of distortion, which look very much like timing jitter. And so you can get all the clocks and everything right only for a little bit of correlated jitter to creep in through that stage. My experience has been that needs to be very, very carefully designed. And in many systems, I think there's compromise there, which is one of the reasons you do hear differences between CD players, even though they might use on paper high-performance D to A converters. The output of these signals are then taken directly to a power amplifier, which then drives directly the individual drive units. And one of the big virtues of an active system is that there are no passive parts to lose power or add nonlinearity between the power amplifier and the loudspeaker. Also, the signal being spread in spectrum means that the actual amplitudes of the signals here and here are reduced. So the power rating of these amplifiers need not be quite as high as having just a single amplifier driving a passive system. So although you end up with two amplifiers, they can often be rated at lower power with lower current capability. And the very tight coupling between a low output impedance power amplifier and drive unit are also important, because you get much better dynamic control, particularly in the mid-range of the drive unit, which often gives you enhanced stereo presentation and more immediate sound. In a typical passive system, well, I say typical, that's not true of really high quality systems, but in lower quality systems it can be a compromise. The input impedance of a loudspeaker, particularly at low frequency when it's being driven hard, that impedance can become nonlinear. So if you've got a passive network here, there is extra nonlinearity because of the modulation of the input impedance of the drive unit and the interaction with the crossover. When it's directly driven, you lose that dependency. It doesn't make it perfect, but it takes out an extra element of distortion. So in this particular approach to a digital system, well, a digital and active system, there are a range of advantages. Let's just very quickly go through them. Obviously, you can use a universal hardware. It's very easy to software tailor it. You can use embedded systems. Simple system replication. Once you've designed your filter, providing your drive units are consistent, you can replicate these as many times as you want, and there's no thermal drift. Digital gain controls are possible. Of course, you need to dither properly to minimize distortion in such a process, but digital gain controls can be extremely accurate. The impulse responses of all the filters can be properly time synchronized. They're not going to vary as they might with an analog filter due to component tolerance. Not particularly sensitive to temperature and supply rails. Obviously the D to A converters and IV stages can be, but certainly the DSP isn't, provided it's within its operating range. You can match the filters very carefully to the individual drive units, so that's good news. You can have near-theoretic crossover filters. We could argue what theoretic crossover filters are, but you can design accurate crossover filters which properly mesh together. Well-controlled polar response. Inevitably, when you have a crossover, there is some frequency region where you get contributions from both loudspeakers, and that causes slight irregularity in the polar response in the far field, and that can be not completely eliminated, but you can certainly, by choosing well-designed filters, you can help that situation. I mentioned before low intermodulation distortion because the signal has been spectrally split between D to A converters. One has, and this I think is a very important aspect, actually minimize the amount of analog electronics. There is still some, there is still the IV stage, there is still the power amplifier stage, but it's reduced to a minimum. And I'm a great minimalist believer. Every stage of analog amplification and processing is a stage of degradation. The best philosophy is one of minimizing these critical circuits and then designing them to be high performance. But you don't want to use any more than you need to. So you can get very good transparency built into those circuits. Because the loudspeakers see simpler loads, we have efficient amplifier operation due to lower reactive loads. And you've got this important link between close coupling of the drive unit and the amplifier compared with a passive system, which tends to lead to better dynamic control with lower dependence on drive unit nonlinearity. So this is one approach to starting to digitize a loudspeaker. It's one which is quite widely used, I think, these days. Not so much in the consumer market. There are companies like Meridian who use DSP and have been very successful with that, and studio systems use it too. But there are potentially great advantages if it's done properly. Of course, you can do it improperly as well. Right, let's try to get a little closer to what we might mean by a digital loudspeaker. Because in everything I've said so far, the transducers are still clearly analog. Now, some very interesting work, again from B&W, was instigated a few years ago, And for those of you who are interested, this has been published in the AES, so if you do a search there, you'll be able to find this work. There's been both stuff in the journal and also presented at conferences. So I would, if you're interested, I would strongly recommend you go and read this literature. Now, the approach B&W have taken is quite an interesting one. And the idea was that because we're dealing with digital signals, how can we couple those digital signals more closely to the actual drive unit? So the concept here was one of using multiple coils, initially at least, on the speech coil. And the D2A converter actually produces currents which are then applied to those coils, and in classic D2A converter jargon, those weightings are binary weighted. So I think it's very easy to conceptualize what's happening here. By choosing the right combinations of weighted currents, we can feed signals to the loudspeaker which will sum to produce the D2A converter. So somehow we have integrated function of D2A converter with the loudspeaker. Now, this does have quite a few problems. You can imagine, as with any D2A converter, which is based on this type of binary division, if there's imprecise matching between these currents, obviously there will be differential distortions introduced in the conversion. And also the problem that because the coils are not physically in the same space, when you have magnets associated with them, again, there will be different sensitivities across the coil. So in practice, there's only so many currents that you could use. So there is this question, how do you then configure these currents in order to get an appropriate dynamic range? But concept, I would sort of argue that although we're getting now much closer to a digital concept, the actual position the loudspeaker takes is still very much defined by standard analogs. And so it's sort of not quite what a digital loudspeaker maybe should be. Although I think it's a very interesting idea and it will have potential. And it may be that some evolution of this technology is the first to get into the marketplace, because it builds strongly upon technology which is already widely understood and available. So that just indicates, there's a reference here, volume 48, number 6, June 2000, where there's a paper describing this. And again, you can see the coils being used, multiple coils. This is the electrical domain. This is the mechanical domain, coupled by the BL factor of the loudspeaker. And there's various factors discussed in this paper. So those of you who are particularly interested in this, I would point out to this particular paper and the related ones. But the journal here is AES, volume 48, number 6. And this particular work was in 2000. But there have been later publications with more advanced ideas. So we're going to ask the question, what really constitutes a digital loudspeaker? I still don't think we've quite defined it yet. You're probably all familiar with the Super Audio CD format, which uses 1-bit coding using a technique called sigma delta modulation. Sigma delta modulation is a technique of taking a digital signal, or an analog signal for that matter, and converting it into a high-speed streams of ones and zeros, normally clocked with a constant sampling rate. Typically in DSD, this is 64 times Nyquist, Nyquist being defined as the 64.1 kilohertz sampling rate of CD. So we're talking around about 2.8 megahertz sampling rate if we were to use a direct DSD code. But just conceptualize the idea of strings of ones and zeros. In the previous example, we had multiple coils. If we use DSD type coding, we only need 1 bit, so 1 coil. Now, if I feed that 1 bit of information directly to the speech coil, albeit the drive unit is still the same, the drive unit will act as a low-pass filter. It has inductance. The clock rate is sufficiently high that the natural inertia of the drive unit will act as a low-pass filter. So is this a digital filter? Certainly if I put an actual low-pass filter in, then it clearly isn't, because if you connect a DSD player to a standard loudspeaker, the filter converts it to analog, and it works as a conventional analog system. If I take that filter away, we're getting closer to digital driving a loudspeaker, But again, the loudspeaker is simply averaging the bits, and you could argue it is still fundamentally an analog process. So that's not very helpful to us. Let's have another look. That represents what I've just said. One case, 1-bit sigma delta modulator converting the signal, one with a low-pass filter, one without. Would certainly work. Probably work very well, because there's very little circuitry there. But I'm still saying, is that digital? I don't think it is quite, although it's getting close. Let's have another look. Let's now look at these ones and zeros coming out of the sigma delta. If we've got a filtered version, either by using a low-pass filter or by just using the natural inertia of the drive unit, then we would expect the cone position to be averaged in some way. Here's the bit stream, 1, 0, 1, 0, etc., and it will average it. I've slightly exaggerated, but you can see the effect. Now let's imagine we had an actual drive unit, whatever it is, piezoelectric, whatever, which has a very fast response time, so that it can almost follow the individual ones and zeros. So if we now looked at cone position when applying the signal, we might see something approaching an exponential rise, but by the end of the pulse, this has got very close to a quantized level. Now, nothing can move instantaneous, so whatever we do, we're not going to have, you know, a step rise in position. So some filtering is going to be there. So this is now, I suggest, getting closer to what I would call a digital loudspeaker, where the individual elements can be switched on and off, such that maybe the cone position follows that bit. Now remember, inertia is the key. So we're now starting to talk of something which is going to be tiny, not like a conventional drive unit. It's going to be shrunk right down till it's almost nanotechnology size. Something very, very small, so it can respond very quickly. I suppose the nearest analogy I can think of is something like the Texas DLP chip, which is used in video projectors, where you have very tiny moving parts, which can obviously move pretty quickly because they have low inertia. And that's the sort of concept. So maybe this gets a little bit closer to how we could visualize a digital speaker, one that has sufficiently fast response that its position effectively becomes quantized. Okay, now I'm not going to tell you how to design one of those little elements because I don't know. What I'm going to assume is that there is some means of producing a small element which we can actually control the position of and address that digitally. It may be a piezoelectric device, it may be some other technology, some nano motor type technology, which can rapidly move that surface. Tiny surface, remember. Now let's say we could do that. And what sort of advantages might accrue from such a structure? Well, there were 2 papers which were in the AES, so you can read these afterwards. I called this first paper a smart digital loudspeaker. So I was curious to say, if we could make such a tiny element, what sort of properties might it have? Now, the sort of properties we're interested in is obviously trying to achieve low distortion. But I was quite interested in this, in seeing what sort of beam formation we could achieve. So I was interested in the possibility of producing a loudspeaker, like a phased array, which could direct the acoustic field in a particular direction. And using DSP, dynamically control the direction as well. And indeed, you could have multiple beams pointing in different directions. And then I want to make some observations on what sort of geometry such a structure should have, because there is a need for low distortion. There's one fundamental difference when we look at these concepts. In a conventional loudspeaker, it is quite normal for the cone not to act as a piston. Often the attempt is there to make it pistonic, but in practice there will be vibration and bending occurring in the surface. If it's properly controlled, we get well-controlled motion within the cone itself, and it's not a fundamental problem. But the cone itself is not necessarily completely rigid. So the idea that different parts of the cone can actually move differently depending upon the input frequency is not an alien concept in the terms of an analog. It happens, and if the equations which control the motion are linear, it doesn't introduce distortion. It might introduce some frequency response errors, but it doesn't introduce nonlinear errors. Now, when we consider a digital loudspeaker, something slightly different happens. There may well be frequency-dependent effects. But what happens is that the surface we're going to generate, and I like to think of it as a sort of digital controlled surface. Imagine we've got this surface where each element of the surface can be controlled in terms of its micro position. So we actually have the ability to address the physical position of that surface. So when we feed signals to it, it may be that the way the signals are fed to the surface are frequency dependent, but it may also be that the way the signals are fed to the surface are signal amplitude dependent. So you can envisage a quiet signal maybe only occupying one part of the diaphragm of the surface, and a louder signal, because we want to displace more air, occupying a larger size. Now, if such a structure were implemented, a surface which is dependent upon the amplitude of the signal will produce distortion. That is not a linear process, such as a frequency dependency on position. So, when I say make observations, it's that effect which I want to make observations on. Are there any geometries which will be less sensitive to this position-dependent amplitude type of signal which we may wish to feed to the surface? Anyway, let's have a look at what the first concept is. Now, this is really very conceptual. Imagine we have a controlled surface, and the surface is made up of this patchwork of elements. And each element is itself made up of another patchwork of smaller elements. So if we take one of these things, and I draw it larger here, it looks possibly like, it may not be a checkerboard, but I've represented it here as a checkerboard, where each element of the checkerboard is itself a small radiator. So there are individual clusters of these things. So the idea is that you would take something like this, which has a number of small exciters. What sort of geometry am I talking about? Well, maybe this is like 1 or 2 centimeters by 1 or 2 centimeters. That's the sort of scale I have in mind. Maybe smaller. I think there's problems if it's bigger. Each of these elements then has some signal processing, and I'm going to say more about signal processing in a moment. I'm going to work on sigma delta modulation, although it's going to be multi-level sigma delta modulation, not binary. There'll be some intermediate processing, which I've called a data scrambler, which is going to then feed these binary signals to this surface. So at a very primitive level, this is the sort of thing I would expect to see. Some sort of oversampled noise shaping circuit, some sort of data scrambler feeding signals into one of these microarrays. Of course, these would then form a larger patchwork, and each would have its own dedicated noise shaping process, and at the input there would be a set of array filters which, if designed properly, could, in theory at least, produce beams of different widths and different directions. So there's a color picture of the concept. Maybe you could make an integrated circuit of this thing where the processing is put into the backplane and the elements, I've shown them as multi-level, maybe some piezo-based or some suitable device which can activate the surface. So these surfaces can be positioned very rapidly in amplitude, and the processing is put in. Now, if you could make the circuit like this, they could then talk to each other on a suitable digital bus, and you could make up a large patchwork, as big as you like. Now, let's talk about beam steering. Beam steering is very much like the type of beam steering you would find in a radio frequency application, synthetic radar, whatever way you get control of the beam. However, I advocate that the audio beam steering is somewhat more difficult than at radio. At radio, often the range of frequencies which you're trying to transmit is actually a small fraction of the carrier. So this means that the range of wavelengths which the array has to cope with is relatively restricted. Now at audio, although it's much, much lower in frequency, if you actually think of the range of wavelengths that you have, you're going from something which might be a fraction of a meter, centimeter or whatever at high frequency, to something which is several meters long at very low frequency. The range of wavelengths is extremely high. So the synthesis of such a system is a little bit more tricky, not impossible, but a little bit more tricky. So to make life easier, I'm going to consider just a one-dimensional version of that two-dimensional array. In principle, it can be extended to 2 dimensions as well, but let's just look at how you might go about solving the problem in 1 dimension. So I'm going to imagine we have an array made up of little radiating elements, each spaced at g, and making up an overall parameter which I've called width, the width of the system. Now, how many of these things do you need? Well, it turns out that at high frequency, the spacing is the high frequency range of the system is determined by the interspacing of the individual drive units. If we want high frequency, you need the drive units to be closer together. If you think of it in terms of sort of Fourier theory, it's really an aliasing distortion problem, albeit in the spatial domain. So it is determined by the number of drive units. The higher the frequency, the closer together they have to be. At low frequency, on the other hand, the ability to steer the beam is determined by the width of the array. So the lower in frequency we go, the wider the array has to be in order to steer these in the beam. So once you've determined the bandwidth of operation, you can work out the minimum number of elements that you need to solve that problem. So how do you design those filters? Well, there's a little definition of what the terms are, just confirming what I've said. Let's skip on a little bit. Let's look at this picture. It turns out that the design of this can be viewed as the design of an FIR filter. Let's imagine we set up this array, and I fed an impulse to each drive unit. Wouldn't do this in practice, but let's imagine we feed an impulse, and the response of this was infinite. So what we see is an FIR filter. If I'm listening off-axis from the array, then obviously the drive unit which is closer reaches me first, whereas the drive unit which is further away reaches later. So we've got these little acoustic impulses. Each drive unit in turn produces that impulse. So if we imagine we had infinite bandwidth, which of course we don't, but if we did, we would see an impulse response something like this. Now, unlike an FIR filter, the difference here is that the sampling interval is actually dependent upon my relative position to the drive units. If I was to sit on axis at a sufficient distance, actually the time difference goes to 0. The sampling rate is like it's infinity. If I stand well off axis, such as I'm here, then obviously the impulse response gets spread out. Now, if we design this impulse response to be a low-pass filter, you can see what happens. If I'm standing off axis, as I move away, the impulse response gets longer, which is equivalent to the cutoff frequency of the FIR low-pass filter getting lower. And if I move below the cutoff frequency, the signal gets attenuated by the filter characteristics. And so we go into the stop band of the polar response. This sort of illustrates that. The top trace looks at a fairly well off-axis position, and this might be, if this was a sin x upon x response, which it won't be quite because the array is finite, we might get something crudely, as I've drawn, as a rectangular frequency response. In practice, it won't be as sharp as that. If I then move closer on axis, the pulses get closer together, and the bandwidth increases. So if I'm producing a signal, say at 5 kilohertz, which is sitting somewhere here, as I move along, as I get closer to the on-axis position, the filter bandwidth changes, and we can move I'll draw it here, from the stop band to the pass band of the filter. So the physical position is a bit like changing the sampling frequency in effect, although it's a spatial effect. And so if we move to the point where we're in the stop band, we get high attenuation. And if we move into the region where we're in the pass band, the signal comes through. Now, the difficulty is, as you can see, that depending on the position, that this frequency will change. There'll be a frequency dependence. If we did this design, let's say this was 10 kilohertz, and we move a little bit one way, stop band, a little bit the other way, pass band. If I now go down to 5 kilohertz, you can see I need a different filter design because the cutoff frequency is up here. So if I just use the fixed set of coefficients, then the filter characteristic is going to be such that the polar response will change dependent on frequency. Now, in terms of this filter, which I showed here, what this actually tells me is I've got to go through this process at each frequency over which I'm going to use my array. And for each frequency, I've got to decide a dedicated set of coefficients to drive these elements so I get my appropriate FIR filter. So as the frequency changes, I need to readjust the cutoff frequency of this filter such that the transition always occurs at the same frequency. And, at the same angular position. So these coefficients, which are now going to drive my FIR filter, are actually frequency-dependent coefficients. And so in simple terms, what you have to do is at each discrete frequency, you could, for example, calculate what those coefficients have to be. And if you calculate enough of them, you can then use interpolation to work out what the coefficients should have been in intermediate space, and you end up with a transfer function for each of those boxes, which is what you'd have to dial in for a particular frequency response. So this is the sort of thing we might do. This shows the plane of the array, and this shows a beam of given width. And by changing the cutoff frequency, by adapting the coefficients in the filter, we can control the width of that. So it's possible, if you've chosen enough elements in the array, to change the width all the way to very nearly 180 degrees up to something which is quite narrow. So that's a very positive feature of this approach. If now we want to tip that response, and not just control its width, but we actually want to tip it off axis so we can actually make it beam in a particular direction. One way of achieving that is to add specific delays in each signal path. So the actual beam itself gets tipped. And you can see a sort of geometric construction here, which we could work out from these path lengths what sort of time delay you'd have to introduce to offset the beam, such as that, for example. So we now have the ability to control both the width and the position of the beam by changing the coefficients in the input to each element. As I say, you do the coefficient design at a discrete number of frequencies, and I've shown this represented here. And then if you make enough points, you can interpolate to get the smoothed transfer function which you require. Then you synthesize an appropriate filter in each signal path. But it's an FIR filter with frequency-dependent coefficients. That's the difference. And they have to be frequency-dependent because we're covering such a wide range of frequency in terms of wavelength. This represents a simulated result from an array. I seem to remember, I think if I recall, there were 64 elements in this array. And I've shown two examples. In fact, once you've got these coefficients, you can superimpose lots of inputs. So you don't just have to have one beam, you can have many. So there's all sorts of possibilities in steering beams in different directions, carrying different messages. And here's a fairly broad beam, here's a fairly narrow one. And it shows it in 3D here. So you can see frequency along here, angular position this way, amplitude vertically. And you can see the two beam widths. At this point, this is the top end of the frequency spectrum, there's just the onset of aliasing distortion. So the polar response sort of gets replicated, and so we get a false lobe appearing. So that's, if you look at this, it's only right at the very top end of the frequency spectrum. Now I said that the lower frequency limit was determined by the width of the array, and interestingly, that's pretty abrupt. You can see we can maintain, theoretically at least, a good polar response down to quite low frequency, but suddenly you run out of steam and the response becomes virtually flat. So that transition region is quite abrupt. The high frequency limit is determined by the interspacing. This limit is determined by the width of the array. And the further down in frequency you want to go, obviously the wider the array has to become. And if you want to maintain the same upper frequency, obviously the number of elements have to increase as well. There's one or two examples that shows a centrally positioned beam. The red blobs are the low frequency end where the polar response is spreading, which is into this region here. You can see these ripples appearing. Now these are actually false. I told you this was computed at discrete frequencies, and the consequence is that the interpolation isn't quite right. So you can see a little bit of ripple appearing at the sort of frequency at which interpolation was performed. Obviously, if I hadn't been so lazy, I could have computed more samples. You only have to do this once. So if you're really doing, and I've deliberately left it like this so you can see the effect, but you could use other techniques or simply use more sampling points and eliminate that problem. It isn't fundamental. You can even get an omnidirectional response. Now, something which comes as a slight surprise, some of you may have looked into NXT technology, which is the distributed mode loudspeaker. And it's actually the DML which got me interested in this idea in the first place. Here, you have a two-dimensional surface, which is excited with bending mode, so every part of the surface vibrates. And the design is such that if you were to look at the sort of, in terms of an impulse response, the correlation of impulse response over different elements of the surface, the correlation breaks down very quickly. So you've got almost like all these little elements vibrating randomly, and it results in a diffuse radiation field. By diffuse, I mean that, again, if you took the on-axis impulse response and you moved a few degrees away, measured that impulse response, then performed a cross-correlation, the correlation is low. In a conventional specular loudspeaker, if you do the same thing, you look at the on-axis response, you take the impulse response off-axis, correlate the two, you find there's high correlation. So a diffuse loudspeaker produces a diffuse sound field where the impulse response changes as a function of angle. It almost looks like a noise-like waveform. Now that, a well-designed DML produces almost omnidirectional sound. So I was curious to know whether you could actually design a directional speaker which had diffuse properties. And the answer is I think you can, and this simulation shows a signal which is both directional and diffuse at the same time. Here's the twin beam example. And you can see now the surface is much more noise-like, which is what you get from randomizing some aspects of the filter design, but it still maintained correlation. And I did check out with cross-correlation to show that it does actually break down. So it is possible in principle to make a directional and diffuse loudspeaker. And here are some examples. There's the omnidirectional one. This actually looks much more like what a DML would produce. It would produce a almost noise-like frequency response. That doesn't mean it produces distortion. It's small irregularities in the frequency response. But it has some extraordinarily interesting properties. For example, if you get reflections in a room, because the reflections come from different angles, off-axis angles of the loudspeaker, and the correlation is low compared with the on-axis performance, the reflections tend to be diffuse. So when they interfere, it's more like adding random noise sources together than it is by adding coherent sources. Make the difference between laser light and incandescent light. So if you imagine the cone is vibrating, we ask the question, what is the relationship between what the far field pressure needs to be and what the cone position is? Now it turns out, if you solve sets of green functions and various things, the solution is that far field pressure is related to the acceleration of the cone. Not its displacement, not its velocity, but its acceleration. Now, conventional drive units do this by default. They get the balance right, and so you get a more or less flat pressure response in the far field. So we've got to take this into account. We've got this little vibrating surface. It's displacement driven, but far field pressure is not related to displacement. It's related to acceleration. Now, if we were to look back at our conventional loudspeaker, you can model this as an analog network, and the various elements are probably familiar to most of you. We have speech coil resistance, speech coil inductance. We have the motor. Effect. Force is related to the BL product times the speech coil current. We also have the motor effect, but the back EMF is proportional to the velocity. This is the mechanical surface where force is dropped across these individual elements, and it's actually velocity flowing in this surface. So this is the cone velocity, U. Here is the mass of the cone. Here is the resistive loss of the compliance. Here is the compliance. And these two elements represent the radiation resistance of the cone. Now it's U, but not U we want to control. And it's that which far field pressure must be related to. And remember, far field pressure is related to acceleration. So we've got to control the velocity in such a way that it falls inversely proportional to frequency. So when you analyze this circuit, it turns out that once we're in the mass-controlled region, and assuming there is resistance in the speech coil, then it actually gives us that result. We end up with a passband where the cone is effectively velocity controlled, and so the far field pressure stays constant. But of course there is, if you have something which is proportional to acceleration, as you go down in frequency, the cone displacement gets bigger and bigger. Now you might have noticed in a conventional loudspeaker, at low frequency the cone moves backwards and forwards by large amounts. But at high frequency it hardly moves at all. And that's because of the acceleration dependence. In fact, as you go down in frequency, for every decade you go down in frequency, you need 100 times more displacement to keep the pressure constant at a given listening point. So you either have to have larger displacements or you have to have bigger drive units. And drive units get bigger at low frequency, and they have to have larger displacements. And a little radiating element isn't going to escape these sort of fundamentals. This is to do with the radiation effect. So we've got to sort of build in this limit, and we've got to take account of the fact that at low frequency we don't want ever increasing displacement. So we need to band limit it. So we'd like to see some sort of high-pass filter built into the system, which emulates very much what a conventional drive unit does. So this is the proposal, or at least the suggestion. Let's imagine these two, and if you recognize this, this is time delay, taking the difference between a time-delayed version and the input. These are digital differentiators. So I'm representing air propagation as two cascaded differentiators. So this gives us the pressure will be related to this point, which is going to be the acceleration of the cone. Now, to compensate for this differentiation, which effectively occurs in propagation, if we look in terms of the input being displacement, then in order to get something which we can control with an input and get a flat overall frequency response, we need to integrate twice to compensate for the two stages of differentiation in the air propagation. On the other hand, if we just have two cascaded integrators, we don't get control of the DC conditions of the system. It's going to drift one way or another. So there needs to be a closed-loop feedback system. And that's effectively what happens. Now, in this particular incarnation, I've made the overall response second-order Butterworth, because very often drive units are very close. Not always, but they're often fairly close to a second-order Butterworth response. So, in this system, the error signal, the output of the first difference amplifier, that's M of Z, is actually going to be proportional to far field pressure, PF of Z. And then the control system comes back. So at low frequency, feedback takes control and controls the mean displacement at the output. But at higher frequency, the gain of those integrators fall, and mainly we see two cascades of integrators complementing the two differentiators effectively in the air. So if we're going to quantize the signal, we need to quantize a signal which is related to pressure P. So we need to quantize at that position at the input to P1. So this was the proposal. Now this is getting close to the simulation model which I used to look at the performance of a micro-array loudspeaker, albeit just now one of these elements. So I use multi-level sigma delta modulation. It's really a noise shaping algorithm which is plugged in here. So it has a flat amplitude response, but it quantizes its output so the noise is spectrally shaped by the filters within the SDM. So we quantize at that point. And we note, in fact, that this signal is proportional to pressure. Now, the output of these two integrators is a signal related to displacement. It's the double integral of the output of the SDM. And this is going to be fed to an array. Now, if you imagine you have your array, then when you sit on axis, if you're feeding these digital signals to each of these elements, when you sit on axis, all those elements arrive instantaneously. Not instantaneously, there's a time delay. They arrive coincidentally, because there's no differential path difference. But when you move off axis, the element which is nearer to you arrives just a little bit before the element which is furthest away from you. So in the simulation, I've modeled this by introducing both a element-specific amplitude coefficient, but also an individual time delay, which I can dial in. And this time delay is simply related to the geometry which I choose for the elements. So the advantage of this, once you've got the code running, you can simply dial in different time delays to simulate different geometries. So it's actually quite a convenient way of doing this. And so the outputs of all these simulated elements, this would normally be equal to 1, but if there were differential gains, then you could take that into account by choosing appropriate coefficients. We can add the output together, so I can then investigate any distortion arising from the fact that the time of arrival of each element isn't coincident, or isn't, yes, coincident. And you'll see there's another box marked code which interprets this signal and feeds it to the appropriate elements. So if you imagine the output of this, let's quantize it to integers because it makes it easy. If the output of this goes sort of 1, 2, 3, 4, then what happens is if it's 1, just one element would be excited. If it's 2, 2 elements would. If it's 3, 3 elements would. So I've actually made all the elements equal weight. I think that's a good idea because you can match them fairly accurately rather than have binary weighting, which over a wide range there could be problems. So they're all equally weighted. So as the signal level here increases, more and more elements get driven and the signal level on the array arises. But of course we can take into account the arrival time. So that's the basic simulation structure. Quantization is by multi-level noise shaping because we want to keep the number of bits here as low as possible. So by noise shaping, you can trade off the number of levels against sampling rate. So we're going to use a sampling rate. In my simulations, I used about 16 times over sampling. And this allowed the number of levels to be dramatically reduced. I mean, had this been, 16-bit code, we'd have needed a really vast number of elements. So we're trying to keep the number of elements down by quantizing the signal. And remember that if this signal is quantized, then when we integrate these two signals, the output here is also quantized as well. The structure for a multi-level noise shaper is a typical feedback network. I of Z represents the input signal, O of Z represents the quantized output signal. We can think of the quantizer, if it's dithered, pretty near to being an additive noise system. It's multi-level, remember. A of Z determines the closed-loop transfer function. and achieves the noise shaping. Now, analyzing that, you end up with this expression. I've included a feed-forward path, which actually makes the signal transfer function theoretically 1. So we end up with the output being equal to the input, so there's no effective modification of the input signal, but the quantization noise, which is added in the quantizer due to fairly severe quantization, is shaped by the spectrum, or the inverse spectrum, of the filter AZ. Now, if we're going to achieve low in-band distortion, then we need a pretty radical noise shaping filter in order to get high resolution in the audio band. And I chose, this was actually based on some earlier work I did with binary sigma delta. I chose a noise shaper which I developed for that, which I call a parametric noise shaper. Now, this was designed so that it acts rather like a parametric equalizer. It has a number of integrators, as typically you find in a sigma delta converter, but it's augmented by what I call a parametric filter. They're actually made up of biquadratic sections where we can take a bandpass component and a low-pass component and sum them into the output. So what it does, it's rather like imagine you're looking at the frequency response with a parametric equalizer. You can tune each stage to choose the transfer function you require. So you can sort of, using some human element, interact with the filter and use it in a fairly intuitive sort of way to tune it to the type of transfer function that you would like. And again, there can be 2 or 3 sections. Now, in the simulations I'm going to show, I use 3 main integrators and 3 second-order biquadratic stages calculated together. And to show you the sort of thing that you can achieve, this is the noise shaping transfer function. This is how the quantization noise will be spectrally shaped. This curve is if no parametric equalization is introduced. And hopefully, if I've done it properly, it should have a 60 dB per octave slope. And I think it does. If we look at a decade going from here to here, there should be a 60 dB drop because it's effectively a cascade of 3 integrators. But if you look at the noise present at round about 10 kilohertz, you can see it's quite substantial. I mean, it's just, with 16 times oversampling, it's just not achieving noise which is acceptable. But by introducing the parametric stages and tuning them carefully, I tune them to give notches at just under 20 kilohertz, just over 10, and something round about 7.5, I think it was. And you can see you can pull the noise down dramatically in that region and get a pretty effective signal-to-noise ratio. And using the parametric approach, as to the often the approach where you feed back round pairs of integrators, the noise continues to fall once you're below the frequency region where the parametric stage operates. So, what does it do? Well, there's the noise shaping characteristic of a multi-level system without parametric equalization, and you can see the ingress of noise starting at about 1 kilohertz and rising to something fairly substantial. The red curve represents quantized 24-bit LPCM data, so I use that to benchmark the performance. If we introduce parametric equalization, you can see that I've managed to squeeze the noise down to virtually the same as 24-bit, although this is theoretical. It'd be hard to make a practical system this good, I suspect. Nevertheless, it just about gets there at 20 kilohertz. Interestingly, if we look at the output of our multi-level SDM, with no parametric equalization, the signal spans typically plus or minus 3 quanta. But there is a penalty to be paid that because we've pushed the noise down, it's got to go somewhere, and so this actually extends the distribution of output signals to typically plus or minus 30 levels. So you can see the difference. There is a price. Due to the noise shaping, we obviously need more activity in the spectral noise shape. This structure shows what happens when we include the SDM in a second-order filter. Remember we showed the filter, second-order Butterworth filter. This one's designed to have a cutoff at 500 hertz, and you can see the output stays flat to 500 hertz, and then it starts to fall. Very similar to what a conventional drive unit would do due to its second-order high-pass filter characteristic. We've emulated that, taking it from standard analog devices. This, again, is the histogram of the output, and one point you should note very carefully is that in this case, the input signal is round about 17.8. There's two components at 0.5 amplitude, round about 17, 18 kilohertz. And the output quantization level, this is level dependent. This is what is actually going to drive the array. The signal spans about plus or minus 60. Now, if I keep the input amplitude the same, and I now lower it by approximately a decade, we see the output is increased to roughly plus or minus 5,000. So we need more elements to be activated. But this shouldn't come as a surprise, because we know that far-field pressure is dependent on acceleration. So when we go down in frequency by a factor of 10, you need 100 times the displacement. And that's what we see. So obviously, if you want to go down to very low frequency, things have to get bigger and bigger. That's just a fact of life. You've got to displace the air ultimately. That's just to show that it works when we design for a higher frequency cutoff of 5 kilohertz. So it doesn't affect the noise shaping characteristic, the fact that it's embedded in a second order system. Now remember, in my model I had all those time delays. So by looking at the geometry of the system, we can work out what time delays we need to calculate. So this is the plane of the array, and this is one element which has coordinates PQ0, 0 because it's in the plane of the array. Obviously, from the geometry of that, we can calculate the path difference related to the position of that general element, and thus work out the propagation delay. So whatever geometry I choose of elements, using this construction, we can work out the appropriate time delays. Now, I got some builders to make me one of these, and this picture just shows them assembling a two-dimensional array. It proved topologically to be quite challenging. Not quite sure whether they succeeded yet. They keep walking underneath, which is a bit embarrassing. Right, here's the first geometry I looked at, the obvious one. Looks a bit like the original slide. A simple two-dimensional array. This is going to be roughly, before I forget to say, I think it was 2 centimeters by 2 centimeters. So that's roughly, that sort of size. And it uses 16 elements, multi-level elements, but 16. And there's the general element PQ0. So from that geometry, we calculate the time delays, plug them into the model, and see what happens. Now, the problem is, in practice, of course, each element might have a slightly different amplitude sensitivity, and the path length depends on which element has been excited. So in this system, as the signal gets larger, more of these elements get excited. You might start off with this one being excited first of all, then those two, and so on. So it grows in some way, and there's a problem. With that array, on axis, no problem, because everything arrives coincidentally. But of course, off axis, that's no longer the case. This is 0.1 degree off axis. Bad news. And you can see, due to the way the array is addressed, we now see intermodulation effects. Remember, the signal is being spread out as a function of amplitude. So there is fundamentally distortion in the process. It's a little bit like jitter. It's not quite like jitter, but because the samples are not added coherently, not actually jittering around for one listening point, but nevertheless there are timing elements introduced, and that leads to intermodulation distortion. Now, if you look at a classic noise-shaped D2A converter, one of the tricks they play is to take the output of the noise shaper, feed it to an equal weighted D2A converter, and then scramble the connections, because it assumes that each element of the D to A converter will have slightly different gains. So by scrambling the connections in some random way, those errors, albeit produce distortion, the distortion translates to noise because it breaks the correlation. And so that code block, which you saw in the earlier slide, actually not only assigns the signals to the appropriate element, but it also scrambles them. So it randomizes the connection. And this shows what happens. The net distortion doesn't go away, but it breaks the line structure. It converts it into noise. And exactly the same, there's nothing magic about this, the exactly same thing occurs in many multi-bit D2A converters, the idea of scrambling. So you can see there is rapid degradation, particularly in the high frequency noise of this system due to the noise shaping characteristic. So I would argue that a rectangular geometry is not actually a very good one. It seems logical when you first draw it, and I was quite surprised how sensitive the high frequency noise was, in fact, to this relatively small delay. In fact, when you look at the histogram of the timing delays, I can't read that, I think it's 10 to the minus 9, you've got about 2.5 nanoseconds of time delay across the array. So, another geometry, this one more regular. Now here, what happens is that we have multiple elements clustered in circles. So this circle, all these elements are fed in parallel, and all these elements are fed in parallel. And this time, as the signal gets bigger, first time the inner elements move, then it gets to level 2, the next set move, and so on. So the addition is by causing this thing to grow and shrink with amplitude. But because now we're using asymmetrical structure, if you imagine what would happen off-axis, I would hear, for example, both that element and then that. But one is early, one is late. So the net effect isn't quite so bad as it is with just the random distribution on the rectangular array. So that was the second structure to look at. And it certainly performed better. Now you may think, oh gosh, the distortion is the same, but this is now at 5 degrees, not 0.1 degrees. So we've seen a lowering in sensitivity to that type of noise. So we may be moving in the right direction, but it's still 5 degrees is still not particularly perfect. So at this point, I was almost completely disillusioned and thought, no, no structure is going to achieve that. But I progressed and tried one more. But before we move on to that one, let's just look at the transfer function as a function of position. You can actually look at it in a different way, because what you've got is this distribution of elements. For each element, as the signal grows, you can plot its transfer function as a function of angle, and that's what this represents. And you can see, in fact, there is quite a modulation in the transfer function in the audio band, and it's that modulation, particularly here at 60 degrees, it's very obvious. And you can see there are different gains depending which element are introduced. It's sort of analogous to the type of distortion which occurs in pulse width modulation. There you've got the pulse varying as a function of amplitude, and so its transfer function is modulated, and if it's not done properly, it gives rise, particularly with uniform sampled PWM, it gives rise to the distortion. Well, that process is sort of similar. These three-dimensional plots look prettier, but they show the same information. Now, just before I gave up, I tried this one final geometry. This time what I did was to take clusters of elements, but based on a single radius circle. So what you have to do, imagine, is that you get a number of elements which are grouped in a symmetrical array. So all the light gray ones are fed in parallel. And then the next set is displaced circumferentially. So the next set of elements are coupled together, but they are now angularly displaced. I've already shown 2, but you would populate this depending how many subgroups you've developed. So the question was, well, if you do that, what is the effect on the number of elements in each group, subgroup? Should you have 2? Should you have 4? Should you have 8? Should you have 16? Does it actually offer you any advantage? So again, some simulations were done. This shows the transfer function for just 2 elements, and you can see it's still pretty disastrous at 60 degrees, so that hasn't completely solved the problem. if we move to 4 elements, it's starting to get better. You can see in the up to 20 kilohertz, there's still some modulation occurring, but it is not as bad as it was. And if we go to 8, it gets even better. So for a 2 centimeter diameter ring, 2 centimeters, 8 elements seem to give a pretty good result. And you can see that the transfer function over even up to 60 degrees has hardly changed within the audio band. It's not quite flat, but that isn't the problem. It's the changes which occur which are important. And again, some simulation on noise shaping. That was with 2 elements, 5 degrees, 2 elements, 5 degrees with different numbers, both with and without decorrelation by scrambling. You can see again, the trick has removed the intermodulation products. We go to, what have we got here? 8 elements. Now this is pretty good. 8 elements show that at 5 degrees and even at 5 degrees, it's pretty near perfect. And even at 60 degrees, we are seeing something which is almost acceptable. At 60 degrees, it's still degrading a little bit, but it's still pretty good, certainly up to 10 kilohertz or so. So I would argue that the geometry which gives, or appears to give, least distortion is where the subgroups of elements are actually spread on a constant radius circle. And for a 2 centimeter radius, groups of 8 seem to be about optimum. But we might wish this thing to work in different bands. I've said that as we go down in frequency, you need not only more elements, but you need a bigger radiating surface. So one construction would be to take different circles which are going to operate in different frequency bands. It's rather like bringing crossover networks back, but making all the drive units sit in a sort of concentric pattern. So at high frequency, we'd have, say, a 2 centimeter circle. As we go down in frequency, each band operating with a separate subband, the circles would get bigger. Finally, just some comments. What shape do the elements have to be? Well, circular is certainly good. But if we've got a large array of these elements, then at lower frequencies, the diameter is going to be bigger. And so there's more chance of distortion coming into the system for off-axis positions. Now, if you actually elongate the larger diameter elements, so you make them blob-shaped like this, or elliptical, or indeed you use multiple rings, all driven in parallel, then when you're off-axis, it acts rather like a filter. Because it's spread out in the radial direction, it actually attenuates the higher frequency concept. So if you wanted to have a large diameter array which only operates at lower frequency, but remember this is noise shape, so you're actually feeding broadband noise into the system, you want the high frequency noise to be attenuated. And this is a method by, it's effectively an FIR filter in a way with 3 equal coefficients, but it can add a degree of high frequency smoothing. And that's supposed to represent what it is. So here we see a fairly large 16 centimeter ring with, I think, 3 rings, and you can see that at high frequency, the actual quantization noise has been attenuated. So you can get some advantage by using elongated arrays, and of course, by using several clusters fed in parallel for larger diameter, you displace more air, which you obviously need to do at a high frequency. Right, we have a blank screen. That's mainly the end of what I want to say. So what I've really proposed is not a total solution by any means, and I'm not even going to start to pretend that it is. But what I've tried to do is exercise some thoughts with you as to if one was to conceive of a digital loudspeaker with these elements, what are some of the sort of fundamental issues which you'd have to consider? How many elements would you need? What sort of signal processing could you be? How could you go about steering these arrays? What are the consequences of off-axis distortion when you have a system which distributes a signal across a surface which is amplitude dependent, which is slightly unusual compared with its analog counterparts? So my main conclusion, geometrically, is that the circular array of subclusters, all at the same radius, is some point where one would want to start looking at seriously for a practical geometry and then evolving that geometry. It is certainly better than the rectangular array. It is certainly better from a circular array where things pulse and grow from the inside to the outside. So that seems to be my conclusion. So if, many ifs, you're all going to throw up your arms because I haven't offered you something you can go and buy tomorrow. But I think this will take a long time, but I think the world is probably now interested because of the way nanotechnology is developing. Obviously, integrated circuitry can be introduced. That isn't a fundamental problem. And the idea of intelligently controlled surfaces to produce loudspeakers with the potential, for example, to steer the beam for all sorts of applications which would follow, and having multiple beams from one surface too, I think is potentially quite an exciting thing. I can see quite a wide range of applications, hopefully for high-end audio, but I suspect these things find their way into things like advertising in shopping malls before they find their way into high-end audio, should such a system become feasible. Thank you very much for your attention.
Professor Hawksford,
yes.
Just another question. Is this the theory behind the Yamaha DSP loudspeakers?
Yes and no. I mean, as far as I understand, on the Yamaha DSP speaker, they use conventional drive units. What they do is to use an array. It's a very clever system. So it's probably one of the first and successful applications of array technology. They use a limited number of drive units in an array. They synthesize a number of beams. The idea is that you can use this single array for surround sound. And it does it by generating probably 4 or possibly 5 simultaneous beams. There'd be direct sound, and the beams are directed to reflective surfaces, which then give the impression of being surrounded by sound. So I would argue that the concepts of beam steering are clearly in that system. Obviously, it's limited because of the number of drive units, but even so, it's still pretty sophisticated. So it's got the beam steering elements and those concepts built into it, but it is purely an analog system. There is no attempt, to my knowledge, of using the drive units in any way which could be described as a digital speaker, although I think it's a very elegant system. So yes, I think it's a most interesting one. I've only heard it on 1 or 2 occasions and not under, so it's obviously not going to be the same as having discrete sources, and it is very environmentally dependent because you need the right reflection and right geometry. But you know, it does give a single box solution which gives a good sense of ambience, so full marks to putting that sort of processing. It's very much the starting point, I think, of this type of technology. And I hope that, you know, more sophisticated systems are developed in the future.
Rankenheim says some experiment on steerable array. I don't know how successful. Has it been applied anywhere in the world?
Again, to my knowledge, there hasn't been a truly digital loudspeaker approach. People have speculated on how to do it. There have been certainly attempts at producing phased arrays. Maybe the closest is in what's called wavefront reconstruction. Now, this is something in Germany they've been very keen on, where you effectively use large panels of large number of drive units. The effect here isn't quite so much to steer the beam, but it is to create a wavefront in the listening area which is very close to the wavefront which would be experienced at the input end of the system. So it does it by having very large numbers of drive units, and it's called wavefront synthesis. And those sort of experiments have been very successful. Now, there is clearly a relationship between beamforming and wavefront construction. It's not quite the same, but you could take I can't see any fundamental reason why, if you had such an array speaker, you couldn't configure it to actually steer beams. If you had a narrow beam in the input space, it would probably map to a narrow beam in the output space. So yes, that's the nearest I've seen, and that's very successful technology. There's also been a synthesis between using DML panels to reduce the number of channels that you need and the sort of wavefront synthesis construction, because you get better integration between the radiation from the various elements. So I watch this space, and particularly with sort of object-coded MPEG type coding, where you can start to very efficiently encode the channels of all the signals you've got fed. You know, if you're looking at in pure linear PCM, you need a huge amount of data to feed all that information. But in the real world, there's high correlation between all the signals going to each element. So by using appropriate coding techniques, I think the bit rate can be kept down. And I haven't looked at it, but my initial guess would be that the new MPEG surround concept has the right ingredients to encode this sort of type of signal. It's the idea where all the signals are almost the same, but they vary slightly in amplitude and delay, is exactly what MPEG surround is for. So you could envisage a system where maybe you have 100 or 500 channels actually very efficiently encoded with a bit budget which may only be like double that of a standard stereo system. I'm guessing, I haven't done the sums, but that's where I would start to look at efficient coding techniques for such structures. I think that's a very exciting possibility.
Any more questions? Maybe you can tell us, predict, when will we see the first truly digital loudspeaker?
They probably already have one in Korea or someone. I really don't know. I think there's such an expansion taking place. I mean, what excites me is the developments which are taking place in things like nanotechnology and the ability to produce very small mechanisms. I mean, a few years ago, if you'd said that you could produce an integrated circuit with 1 million or whatever it is moving mirrors, I would have thought that's a very hard task. But now it's commonplace. And I think that's the impetus. It obviously needs a big investment, but you've got to get to the point where you can manufacture these elements as cheaply as any other integrated circuit. Then it becomes possible. Maybe it needs to be application driven. Maybe it needs someone to say, I'm going to build this for a large football stadium where I actually want to beam signals in different... So it's some grandiose project which would give the impetus to actually do the development work. And it's still, I have to say, in my mind, it's still not obvious that this necessarily translates into a better speaker than is done by traditional analog techniques. I think there's a long... But it's taken 100 years to get the analog speaker working properly. So, you know, it will probably take 100 years to get the digital one working properly too, I suspect, if at all. But, you know, you've got to start somewhere, and I think it is the idea of integrating the conversion at the actual point where electrical to or acoustic transduction takes place is an interesting area, and it is a challenge, and it is a question which we need to answer. Can it be done? If the answer turns out that actually the results are poor, it's not economic, fair enough. But, you know, you have to try first. And I'm fairly optimistic that in practice, people will think of developments and ideas which, you know, aren't yet penciled, which will make this thing proper. I've only touched on the surface, I think. But I'm really just answering one question, and that's to do with what effect does geometry have on polar response and distortion. You see, if you said that each element had its own sigma delta converter, now think about it, you've got, I don't know, maybe 500,000 of these things with 500,000 parallel sigma delta. The problem actually goes away because the quantization noise which you'd feed to each element isn't correlated anymore, so you don't get the polar problem. So there is a solution. The reason I see a problem with this is that I try to reduce the number of sigma delta modulators, if you like, to 1 per chip, so that it's really a question how you then address the elements within the chip. But if you allow yourself more and you correctly dither so that the correlation is broken down between the adjacent elements, then the time delay problem disappears. And that may be the proper solution. But, you know, you take it, at what point do you change the amount of signal processing you need? So that's another question. It may be that there's a sort of intermediate solution which is better. So I've just looked at it in terms of an individual thing. And maybe the extension is that you do it for a single ring, when you have multiple rings, and each one of those has its own dedicated SDM. But ultimately, it's how many circuits you can afford to put into the system.
Given the small size of these the ICs, if they can be manufactured, Have you given any thought to, the volume, the intensity
Ooh,
of
massive.
the
If I had made money for each circuit that this would sell, I'd be very rich. I think the sort of physical size of one of these, it depends how it's configured. If you're going to make a phased array, and obviously you need a large number of small elements, because they all need to be physically the same. And I think somewhere around about 2 centimeters square is the right size. If you're building something more akin to a single loudspeaker, where it actually grows concentrically, then that's a different problem. But then the downside is that as it gets bigger, you need a different geometry for each array. And so you lose the economy of scale. Having something which is based on just one entity, you can tile it to any physical size you like. If you need something where, the circles are getting bigger and bigger, yes, okay, maybe you can make a big 16 centimeter square circuit with the right geometry. Perfectly feasible. But what fun is that at the end of the day, this surface has to move, and it has to move in a similar way to an analog transducer. You can't break the laws of physics. You have to display so much air at so many frequencies, and that's the life. I mean, ultimately, maybe you'd stick one of those big horns on the front to make it more efficient, so it would look more like an old-fashioned analog loudspeaker system. But yes, I mean, at the moment, you see, power has become so cheap that people don't worry about efficiency anymore. So you lose sight of what efficient transduction can do. And when you hear a really good horn-loaded loudspeaker, because the power amplifiers are not heavily stressed, and because the moving parts don't actually have to move very much within them, the sound has it couples to the air in the room in a way which is quite tangible. I mean, I've heard those avant-garde speakers. They're not the most neutral sounding speakers, but they do things in a magnificent way. And the one I saw I think it had an 8-watt Class A amplifier, which wasn't much bigger than a matchbox. And you could hardly stand the volume in the room, because it was probably producing 2 or 3 acoustic watts, which is very loud. That's a fact of life. But it needs space. Low frequency needs huge horns. You can't escape that. Anyone can think of a way of making it very small and efficient. You'll make a fortune. But I don't think physically it's possible. People attempt to fold horns, by folding them round and round, but something gets lost. You really need the big one.
Any more questions? If not, let's thank Professor Hawksford again.
Thank you very much.